last class we introduced the concept of space vector, and for a sinusoidal excitation the voltage space vector will rotate with uniform velocity, and the tip of the vector will trace a circle. So, in our PWM operation we want the average variation of the voltage space vector. Now, let us draw our inverter. So, inverter is, this is our DC link voltage, and you have 6 bidirectional switches. Okay. Here we connect the A, connect B, here we will connect C, such that the load, 3-phase load, when it is represented, let us take this is A, B, C, such that IA plus IB plus IC is equal to 0. That means, for a 3-phase system, this shows the triplet currents are absent here. So, triplet currents are absent here, that will not be contributing to the flux space phasor. So, we are only talking, the moment we are talking about the space vector, we are talking about the harmonics for which the sum of 3 phases should be equal to 0, whether voltage or current. A plus VB plus VC is equal to 0. Now, these are bidirectional switches. Okay. Diodes will be there, that I have not marked it before, just for clarity. Okay. Now, if you see the ABC phases or the poles, A can have 2 positions, either to the top, to the bottom. Okay. So, this will represent as, if top switch is on, top on will mark as 1. Okay. For the bottom switch is on, will mark as 0. So, for each pole there are 2 states possible, either 1 or 0. So, there are 3 poles. So, you will have 2 raised to 3 states, 8. Now, what are the states? Let us see. So, this is only possible using these combinations of, alternatively using these 8 states, we have to generate the PWM waveform such that the average variation in the phase will be sinusoidal. So, the switches with the pole, let us say, let us take this way, I will draw it here. So, state 1, okay. Now, this is our A, B, C. So, let us take the conditions 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. As I told, these 2 are 0 states. That means, all the top switches are on the ABC phases will be shorted to the positive limb. 0 means 3, this means all the bottom switches are on, and all the ABC will be shorted to the bottom limb. So, these are called 0 states, 0 inverter states. Now, ABC, let us start with 1, 0, 0. 1, 0, 0 means this A phase will be connected to this one. What about the B and C? B and C will be connected to the bottom switch. That means, bottom device is on. This is 1, 0, 0. Okay. Now, let us take Next is, let us take 110. So 110 will be A, B, C. This is A, this is B, C. So 110 means both A and B is connected to the top. So this will come like this, and C will be connected to the bottom rail. So this is 110. Now let us take 3, the 3. Let us take this is 0, let us take this one 3 is equal to 0, 1, 0. So again we will draw the inverter poles, how it, where it is connected, A, B, C. Now what we are talking about is 0, 1, 0. So A will be connected to 0, bottom. B will be connected to the top. C pole will be connected to the bottom. So this is 0, 1, 0. So 3. Now let us go to the next page. Now let us take the fourth state. Fourth state we will take as 0, 1, 1. 1, 1. So here the inverter poles are connected. So from the pole state 0, 1, 1, it is clearly indicates where we have to connect the inverter poles, that is ABC poles. A will be connected to 0, that is bottom side. B will be connected to the positive. So top switch is on in the B leg. This is 0, 1, 1. This is our fourth state. Now let us take our fifth state. Fifth is 0, 0, 1. Here it will be like this. A phase will be connected to 0, B phase also connected to 0, C phase connected to A, B, C. A phase is connected to 0. By connecting means our bottom switch is turned on. B is also connected here. C is connected to top. This is our fifth. Let us take our sixth one. Sixth one is 101. This is ABC. See, A phase is, or pole A is connected to the top rail and B is connected to the bottom rail. That means the bottom switch is on, and C is again connected to bottom, top here. This is 101, 6. Now, 6 are over. The next are the 0 state, that is 7 and 8. 7 and 8, let us take, that is 111. 7 is 111. That means all the legs are, or the pole A, B, C are shorted to the positive rail. That means A, B, C. A, B, C. So 111. So that means it is connected here. This is connected here. This is connected. So here, if you see here, it's connected here means all the ABC is shorted to the top rail. Okay, this is 0 state. 0 state, inverter state. Now one more is there, that is 0, 0. That will term as the number 8. So here A, B, C. Here all the 3 poles A, B, C is connected to the bottom rail, that is bottom switch is on. This is also called a 0 state. So for PWM operation we can have only during one operation we can only have 1 out of this 8. So, how do you use these states such that the average variation in phase is sinusoidal, or the voltage space vector will tip of the voltage space vector, the average voltage space vector will trace a circle. So, here now let us see if we are in a sequence starting from 1, 2, 3, 4, 5, 6, these are the active vectors. The states 1, 2, 6 are called active states. That means this can only produce a non-zero output voltage space vector. These are called active vectors. Now, before coming to PWM, let us say in the xy plane where this voltage space vector lies, all the 8. Let us take. Let us start with 1, 0, 0. 1, 0, 0. Okay. If it is 1, 0, 0, that means A phase is to the positive rail and B and 0 are 0. So, let us say take a switch sequence like this. A, B, C. A is connected to the top, B and C are 0. Now, let us draw the combined effect of all the 3 phase voltages, that pole voltages, that will give the vector. So, if you see here, this is our A phase axis. A phase 120 degree phase shifted, we will get the B. Then we will have the C. This is the B axis, this is C. So, when A is turned on, A will be, no, A leg is 1, 0, 0, A is connected to the top, B and 0 are to the 0. So, let us measure the pole voltages, okay, with respect to, let us say, the bottom rail. So, A is positive, so this is VDC, B and C are 0. So, B and 0 are, when we are measuring with respect to the bottom rail, the voltage, pole voltage of B and C are 0, pole voltage of A is VDC. So, A is, let us say, this is VDC, the vector will be here, this is the vector. So, when 1, 0, 0, this is here. Now, let us take 1, 0, 0, 1, 1, 0. That means A and B are at VDC. A is here, B is also at VDC. So, the vector sum, this plus B is also positive. So, somewhere here it will come. See, A plus B is minus C. So, along the minus C axis. So, here it will come. This is our vector. So, A here, B, this vector parallel to B 180 degree here. This is 1, 1, 0, vector lies here. Now, let us take 0, 1, 0. That means both A and C are 0, B is 1. So, B is VDC, it will be here. So, all these amplitudes are VDC. This vector, this is VDC. Now, let us next take the next one, 0, 1, 1. That means B and C are VDC. V is already VDC, C is also VDC. So, take a vector sum. It will be negative of A phase axis. Here it will happen. So, the vector is here. So, because B plus C is equal to minus A. So, this is also VDC, this is also VDC. So, here it will come minus VDC. Now, let us take the next one, 0, 0, 1. Now, C is 1, A and B are 0. So, it will be here, VDC here. This is 0, 0, 1. The next one is 1, 0, 1. 1, 0, 1 means A and C are 0. So, it has to be along the minus B axis, because A plus B is equal to minus, A plus C is equal to minus C. So, along this axis, parallel this vector we put it here. So, it will come here. So, if you see here, this is 1, 0, 1. 0, now 1, 1, 1 means all are 0. A is in this direction, B is in this direction. So, parallel. B is also VDC, C is also VDC. So, in this direction. So, it will sum up to 0. That is 1, 1, 1. So, A is also VDC. So, A we added. Then B is also VDC. So, VDC we added parallel to B. Then C is also VDC. So, C is in this direction. So, net will be 0. Similarly, 0 vectors also, all are 0. So, this is the 0 vector state. Now, if you see here, see this diagram, this one is a hexagon, and the radii of the hexagon is equal to the voltage space vector structure for the 3-level inverter. See, here if you say, no sorry, this is a 2-level inverter code. That means each pole can have either this level plus or minus. So, these are called, this is called a conventional 2-level inverter. So, for a this 2 level is with respect to one pole. So, 2-level inverter for the 2-level inverter, all the 6 active voltage vectors lie along the radii of a hexagon. Hexagonal radii is this one, radii of a hexagon. Okay. So, for one cycle of operation, active vector if you switch it will 1, 2, 3, 4, 5, 6. So, this is also 2-level inverter is also called a 6-step inverter. So, when the active vectors are switched, it will take 6 steps to make one complete revolution. This is also called a 6-step inverter. Okay. Now, we want the voltage with the PWM, the radii of the average variation of the voltage space vector or the tip of the voltage space vector should move along a circular trajectory. So, how can generate? So, we can only use these combinations. With these combinations, how do you get a voltage average variation of the voltage space vector for which the tip of the voltage space vector traces a circle with a uniform velocity. So, in this hexagon we can have different circle with a different average variation. This is one circle, this is one circle. Now, what is the maximum circle we can inscribe? That means it does touches these points. This is the maximum radii possible. Now, if you see here, sorry, it has to touch here. So, this is the maximum radii possible. So, radii, what is the maximum radii of the voltage space vector or the amplitude of the average variation for the rotating voltage space vector? So, this angle is equal to 30 degree. This angle is equal to 60 degree. This amplitude is equal to VDC. So, this radii, maximum radii is equal to VDC into cos 30. That is equal to root 3 by 2 VDC. So, this is the maximum radii possible, root 3 by 2 VDC. Now, for let us take a motor drive application. Motor drive application with the V by F control, which we will study later. As the frequency varies, the V also should vary proportionally. That means frequency is 0, V should be 0. When the frequency is 25 and frequency is 50, for the frequency is doubled. So, the amplitude or the radio of the voltage reference space vector should also be doubled. That means within this hexagon, we should have different circles, inscribed circles with the different radii should be possible. Now, how to generate? See, let us draw our hexagon once again, approximate. Okay, approximately I have drawn the hexagon. This is plus 0, 0. This is plus, plus 0. Or, okay, we have used the, instead of plus, we have used 1, 1, 0. So, we will use that one. That is 1, 0, 0, 1, 1, 0, then 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1. Now, let us take for a particular radii, some radii. This is the one we have to generate, average variation of the voltage space vector. Now, let us take for a moment the reference space vector. So, we will say reference space vector, this is a space vector, V underscore we will put it, that it has a magnitude and radii. Let at one instant, if Vs is here, how to generate Vs here? See, if you see here in this hexagonal space sector, there are 6 sectors, sector 1, sector 2, sector 3, sector 4, sector 5, sector 6. Okay. In these sectors, suppose the Vs, the reference phase voltage is in sector 1, and our reference space vector is rotating with uniform speed. So, what we will do, we will sample this rotating reference space vector. So, we will sample, that means sample the rotating reference voltage space vector Vs with what sampling means, there should be a sampling frequency. So, the sampling frequency let be much more than the fundamental frequency, high sampling frequency, Vs at high sampling frequencies, or we can set low sampling periods. That means, we as quickly as possible, instead of it is circle, we will sample it with low sampling periods. Low sampling periods, that means here we are sampled here, we are sampling here, we are sampling here, sampling here. That means, in a sector we are sampled so many times. So, that means, when you sample this one, the average variation is as close as to a sinusoidal. Continuous sinusoidal variation if it required, then we require very high frequency sampling. So, very high frequency sampling, that is its own problem. We have to control the inverter with a very high sampling frequency. So, that will also lead to losses. So, there is a limit with which we can sample it, that depends on the inverter. So, that means it is continuously rotating vector, we sample it with a low sampling period. So, high sampling frequencies. This sampling frequency we can relate to our sine triangle, the equivalent to the carrier frequency, triangle frequency, where the frequency of the sine is proportional to our continuously rotating reference space vector, and the sampling period is proportional to our triangle period. We can relate that. So, when you sample it till the sampling period is over, that means till the next sampling period, we will assume the VS is stationary. That means VS is making in a instead of continuously tracing, VS is making small jumps as shown the dots here. So, that jump depends on our sampling period. So, what I mean here, during a sampling period, once it is sampled till the next sample, we will assume the VS is amplitude and the angle is stationary there. Then this VS we will generate by switching. Suppose VS is in sector 1, we will switch between 1 0 0, 1 1 0 and the 0 vectors 0 0, 1 1 vectors, such that the volt second using volt second balance. See what is meant by volt second balance? Let us take, we have a 10 volt DC. This is our 10 volt. Now I want 5 volt. So what I will do? I will chop this waveform. So 5 volt means 50% duration I will make it on using a switch here at the output where the voltage is required. Then next 50% it will be 0. So it will go like this. So this is the T on period, this is the T off period. Okay? And we want 5 volt. Average value is 5 volt. So in a period T is equal to T on plus T off. So volt second balance, that means 5, if it is 5 volt is there, the area volt second 5 into T on should be equal to, no, so 5 into T, not T on, because 5 is there, it will be there for full period. Okay. Volt second, this should be equal to 10 into T on, because 10 is only for T on period. Okay. So that now the 5 volt is equal to 10 into T on by T. So T on by T is called the duty ratio. So by using this volt second balancing, we can average variation of 5 volt is we can generate. So 5 volt will come chop, then after this one you put the filter and you will get 5 volt here. So filter means harmonics you can remove it and DC value you can you can generate it. So here also we will use the volt second, that means the volt second, that Vs into T, the volt second. See here, if you see, these are vectors, these are scalars here. So we have to take the volt second along the alpha axis and the beta axis, orthogonal axis. So that component of Vs along alpha beta axis, volt second. So Vs for T period, the sampling period Ts, that Vs, the component of the Vs along alpha beta multiplied by the sampling period, that is a volt second of the reference voltage along the alpha beta, should be equal to the volt second of 1 0 0, 1 1 0 and the 0 vector along the alpha beta. So if the volt second is matching, same way we are by switching, that average variation of Vs is generated. So let us see how this volt second we can generate. So let us go to one sector. The same thing we can use it for other sectors also. Other sectors for a particular angle, alpha is the angle with which the start of the sector Vs makes. For other sectors also alpha will be the same, only the switching vectors are different. The periods, let us take 1 0 0 in a sampling period, 1 0 0 is making a period T1 and 1 1 0 is making T2 and T0 period. So T0 period is equal to sampling period Ts minus T1 plus T2. First of the period you will be 0. Okay. Now you have to find out T1 and T2 such that the volt second along alpha beta should be matching. So let us, how to find out this one? Let us go to the next page. So let us draw our alpha beta axis. This is alpha, this is beta. Okay. Let us say it is in sector 1. Sector 1 means this is VDC, after 60 degree another VDC. Okay. So, we are going to derive the general rule. So, we will take the vector, each sector, the start of the vector we will call V1, this will call V2, this called the 0 vector. Okay. Now, this is our Vs, voltage, sampled voltage space vector, which is tracing a circle. During this period sampled, for a particular sampled period, let us make Vs is making alpha with respect to the start of the sector V1. In sector 1, V1 is equal to 100. Okay. Now, let us find out the volt second. See, along the alpha axis, volt second along alpha axis. See, and V1 is switching for a period T1, V2 is switching for a period T2. This is for T0 period. So, volt second along alpha axis is equal to V1 into T1. When V2 is switched for T2 period, what is the volt second along alpha axis? The component of V2 is, this is 60 degree, a sector is 60 degree. So, this is equal to V2 cos 60 degree into T2. This should be equal to, and Vs, we are saying during the full Ts period, sampling period, Vs is stationary there. So, Vs into Ts, and the component along the alpha axis is equal to cos alpha. Okay. Now, what we want to find out? We want to find out during a sampling period. Sampling period is fixed by us, but T1, T2 we have to find out, that depends on the Vs magnitude and the angle. So, we have to find out T1 and T2 for a particular Vs. Vs, that is a voltage space vector, that is a particular magnitude as well as angle. We have to find out T1, T2, so we require two equations. The next equation we can get from along the beta axis. Beta axis. Okay. Volt second along beta axis. See, this is alpha beta 90 degrees. So, V1, when V1 is switched, it will not contribute anything along the beta axis. So, that will be 0. But V2 will be sin 60. That component of the V2 along beta is equal to sin 60. So, V2 sin 60 into T2 is equal to Vs Ts into sin alpha. That is a component of the Vs along the beta axis. Now, from these equations, using two equations, we can find out T1 and T2. This we can solve it. Solving T1 will be equal to, T1 is equal to Ts into Vs. Vs is the magnitude of the Vs. See, here Vs is this is the magnitude of the Vs we are taking. Vs divided by Vdc. Why Vdc comes? The magnitude of V1. Magnitude of V1 equal to magnitude of V2 is equal to Vdc. So, this will, Vdc is equal to sin 60 minus alpha divided by sin 60. Sin 60 is equal to how much? Sin 60 will be equal to root 3 by 2. So, this will come divided by 2 by root 3. It will come. Similarly, T2 will be equal to Ts into Vs divided by Vdc into 2 by root 3. Again, denominator sin 60 comes, it will come to sin alpha. This is the equation. So, in a sector, alpha varies between less than or equal to 60, greater than or equal to 0. That means it varies from 0 to 60 degree. So, we have to compute for alpha varies from 0 to 60, what is T1, T2. This is, and as the Vs traces a circular trajectory, this is true in other sectors also. but only for the alpha. Alpha means alpha measured from the start of the sector, but only the vectors V1, V2 will vary in different sectors. Okay. Now, if T1, T2 we know is T0. T0 is equal to Ts minus T1 plus T2. So, rest of the period T0 period we will switch the 0 state. Now, as we go from 0, V1, V2, that means inverter switchings are there. So, we will inverter switching means there is always switching losses associated with it, because switchings are not instantaneous. So, we want to ensure minimum switchings during a transition. That means as it go from V1 to V2 to 0. These are called sub intervals. That means T1, T2 are called, T0 are called sub intervals. That means the intervals within a period Ts. So, during the sub intervals we want minimum inverter switching. So, how it can be done? Let us go back to our sector again. Let us draw the sector again. This is sector 1, 2, 3, 4, 5, 6. 1 0 0, 1 1 0, 0 1 0. If you see, these are opposite, 0 1 1. So, 1 1 0 means this has to be 0 0 1. This is 0 1 0 means this should be 1 0 1. Now, zeros are 1 1 1 and 0 0 0. Now, in sector 1, this is we are going from. So, minimum switching means how we can go? See, it is done, the T0 period is divided into two intervals, that is T01 and T02. So, T01, T02 will be equal to T0 by 8. That means two zeros are split at the during a sampling period. Let us take the sampling period. During a sampling period Ts, let us take in sector 1, S1. The sequence will, let us start, it is starting from 0 0 0. That is first T01, T01 is 0 0 0, then it will go to 1 0 0. Here means only A phase is switching. Then 1 0 0 to 1 1 0 it will go. So, here B phase is switching. Now, the last 0 period 1 1 0 it will go to 1 1. There is only, that means during a sampling period minimum inverter switching, only one inverter transition takes place. That means, let us take the T01, this is the T01 period, let this is the T1, T2, and next to T0 period. So, if you see here, this is our Ts. So, this is T01, T01 and T01 and T02 are same. This is T1, this is 2. So, in sector 1, we will start from 0 0 0, then 1 0 0, then 1 1 0, then 1 1 1. These are 0 period. And the next sampling interval, when the next sampling interval we will find out T1, T2, T0 in sector 1 itself, but we are the previous state is 1 1. Then we will reverse the sequence. That means the next sampling period will start with 1 1 1, then 1 1 0, then 1 0 0 0 0. So, we will go sequence. If you see here, there is a we can say positive sequence and a negative sequence. This way will go, that will ensure. So, this is Ts period, the first Ts period, this is the second Ts period. So, here we will start with 0 0 0, then 1 0 0, then 1 1 0, then 1 1 1 here. Then the next sampling interval start with 1 1, first is T0, then 1 1 0, then we will go to 1 0 0, then the last 0 bit. So, the sequence, if you say this is the T01, T01, T1, T2, T02. Now, here it will start T02, T2, T1, T01. So, this way it will go. So, that will ensure minimum inverter switching. Now, let us say if this type of switching, what is the volt second, what is the average variation? So, let us see how the switching sequence will be there in sector 1. Let's go to the next page. So let us see the switching. As I told, sector 1. So we are dividing T01. Let's say this is the T0 period. Let's say this is the T1 period. Let's say this is the T2 period. This is the T0 by 2 period. Okay, this each TS period we divide the different color. Okay, then happens the next T0 by 2, T2, T1 and the next T0 by 2. So this is T01, T1, T2, T02, T02, T2, T1, T0 in sector 1. Sector 1 we are starting with 0. So let us take the pole voltages, that is VA0. See here the pole voltage, we have already introduced what we mean by pole voltage. This is A, this is B, this is C. See, when the top switch is on, we measure with respect to the fictitious center point 0. So that means this is VDC by 2, this is VDC by 2. So when the top switch is on, all 0. Now let us take T01 is equal to, we know this period is equal to, okay, we will write with a different color. Right. T01 is equal to 0, 0, 0, this is 1, 0, 0, 1, 1, 0, 1, 1, 1. This is 1, 1, 1. Then T2 is equal to 1, 1, 0, 1, 0, 0, 0, 0, 0. So let us see according to this one how the pole voltages. Now the pole voltages we are measuring with respect to the fictitious center tap. Okay. So when the top switch is on, it is VDC by 2, bottom switch is on, any pole it will be minus VDC by 2. That means 0 means minus VDC by 2, 1 means 1 indicates VDC by 2, 0 indicates minus VDC by 2. So let us take for a general T1, T2 period how the pole voltage waveform for VS0. So VS0 will draw it. We will draw with a VS0 will draw with red color. So during the T01 period, VA will be negative. So the pole voltage is during this period negative. Now T1 period it is positive. 1 because 1. Again T2 period is also it is high. So it will continue there. Then 1 1 means again it is here. So the first sampling period, so that is the first sampling period from here to here. Only once the inverter leg is switching. Okay. The next sampling period again 1 continues. Again 1 1 0, it will go like this. Again 1, okay, next is 0. So if you see here the switching sequence for during the sampling period using volt second, the switching transitions during various intervals, sub intervals are selected in such a way only in a one sampling interval one phase is only changing state only once, even though the space vectors are changing from 0 0, 1 0 0, 1 1 0, 1 1. 4 space vectors are involved, 2 zeros and 2 active vectors. This is for the A phase, that is VA0. Let us draw, this is the VA0. Now let us draw the VB0. B will be, let us take blue. So B again it will start with 0. 1 0 0 means B is also 0 here during the T1 period. Okay, 0. Now here B goes positive, that is 1, VDC by 2. So, it comes during the T0 period also it is like this. Now, next sampling interval also it is like this. Here till T2 B is positive, then the moment last 0 here the T1 period and the last 0 period is negative, that is 0. So, this is the VB0 voltage. Now, let us take the VC0. Let us take green. VC0, that is, this is 0, this is 0, this is 0. Till this period it is 0. Here it will go positive, goes 1, 1. Here it will come down. Again, if you see here, it will go like this till negative. So, if you see in the sector, the pole voltage is VC0 with the space vector PWM, you can see this type of nested waveform. And in a sampling interval, each phase only changing, each pole will change at once. Now, let us find out. So, we know the positive and negative. So, during a sampling period, we can find out the volt second and we can average it by TS. So, in a sampling period, same like what you have done for sine triangle, let us how to find out the average value. Now, let us find out the average values. That means VS0 average. Let us draw the VS0 average. That is equal to, see, either positive or negative, the amplitude is VDC by 2. So, average value you have to divide by TS into, see, during the T0, first T01 period. So, T0 periods are equal. So, we will make it the duration T0 by 2. So, first T0 it is negative. So, it is minus T0 by 2. And then you have T1, this is the period, plus T2. Then during the next 0 also it is positive VDC by 2. So, it will be plus T0 by 2. So, we are taking the duration first is for VS0 average. Now, let us take VB0 average. Again this is equal to VDC to, you are taking the volt second and we are averaging. That means VDC by 2. Here also minus T0 by 2. Then minus T1, because during the T1 period it is minus T1. Then comes plus T2 and plus last T0 by 2. Similarly, VC0 average is equal to VDC by 2 into TS into minus T0 by 2 minus T1 minus T2 plus T0 by 2. Okay. So, during the T0 by 2 period, first sampling interval, if you take all the 3 phases, the pole voltages are in the opposite levels. First T0 if it is minus VDC by 2, in the top side it will be, in the last T0 by 2 is VDC by 2. So, this we can cancel. So, the volt second, the 0 vectors are not contributing to the average variation. It is only by the T1, T2. So, for VS0 average, VS0 average is equal to VDC by 2 divided by TS into T1 plus T2. Okay. And what is for, and what is VB0 average? VDC by 2 into minus T1 plus T2. And VC0 is equal to minus of VS0. So, that is equal to VDC by 2 divided by TS into minus T1 minus T2. In a sector T1, T2 periods are 0, the Vc0 average is equal to minus of Vs0 average. Now what we have to do? T1, T2 in a sector we have found out. For a general angle alpha, that you substitute and we can find out Vs0, Vb0, Vc0 average for alpha varies for 0 to 60 degree, how the variation happens. Then we can also find out how it happens for other sectors, and if you know the average variation for 90 degree, we can repeat it for other sector, because it is circular, average variation is tracing circular space vector. That means the sinusoidal one is, but the phase voltage average variation is sinusoidal. So 0 to 19 is sufficient. So this way, substituting these values into the equation, we can find out the average voltage variation, and from the average voltage variation we can find out whether the average space vector is tracing a circle, or if the average voltage variation for the phases are sinusoidal, then our PWM is achieved, space vector PWM is achieved. So this way, so our analysis shows that the space vector PWM, so appropriately choosing the selecting the T1, T2 for a particular Vs, that is a reference space vector of particular amplitude and alpha. For different frequencies of operation, we can have different amplitudes, and alpha also, alpha varies when it traces the circular trajectory, but the frequency only varies. So this way we can find the space vector PWM can be implemented. Now the question is how to find out T1, T2 and how to implement, and during the T1, T2 in a sector, how to output the sectors. This we will study later. So here we will see, in the next class we will see, let the average variation for a phase Vs0, Vb0, Vc0 is a sinusoidal one. If that is the case, then the voltage space vector will be tracing a circle. So average variation, the average variation of the voltage space vector will be tracing a circle. This we will study in the next class.